Are you ready for some more? It just goes on and on. All right, here we go. Sampling distribution of a sample proportion. So proportion is like 23 out of 100 people really like popsicles, or 72 out of 72 people wish that they had $1 billion in the bank. I don't know if that actually be true. Or like 132 out of 178 people wish, I don't know, whatever, right? They have a blue shirt. So a proportion is some amount over another out of another amount. And so here's like x out of n, where n is your sample size and x is how many have that characteristic, number of elements in that sample that possess a characteristic. And then p here is the proportion of the people that have it. So that's the formula, p equals x over n, whether it's 32 out of 100 or 72 out of 72 or like 132 out of 194 or whatever it is. You're finding a proportion, and that's how you do the proportion. And so we're going to we looked at the mean, doing this like with a sample mean to be a point estimator and approximation of the population parameter mean. Now we're going to do it for a proportion, right? And so slightly different formulas, but pretty much the ideas are just the same. And we're going to get a little bit of reinforcement of doing the z-table thing. So here's the same thing about statistical inference. We don't know what the population proportion is. And we're going to see a little bit of nuttiness about this in a second. But a simple random sample of n elements is selected from the population. The sample data provide a value for the sample proportion. 14 out of 74 people like movies. And then the value of the sample proportion is used to make inferences about the value of the population proportion. And so here is proportion for the sample, that's the notation, and for the population, that's the notation for proportion. And so the sampling distribution of the sample proportion is the probability distribution of all possible values of the sample proportion. And, again, we're dealing with a probability, a sampling distribution here, a sampling distribution of the sample proportion. And the sampling distribution is the probability, so I'm just going to highlight this. Oh, can I highlight it? I can't highlight it. All right, that's fine. The sampling distribution of the proportion is a sampling distribution, and it's the probability distribution of all possible values of the sample proportion. So as we did different samples, we might get different values for that proportion of people in our sample who want something or don't want something or whatever. And those different values will have their own distribution. They can be treated as a random variable. And then we could do probability on that distribution. So just like we did with the sample mean, right? Same thing here. And the expected value of the sample proportion will be equal to the population proportion, which, right, kind of. And then we have this finite versus infinite with a finite correction factor. And this is the standard error of the proportion is that. And it's the standard deviation of our proportions, right? So it's a standard deviation of our proportions. It's known as the standard error. And this is how you calculate it right there. The sampling distribution of the sample proportion can be approximated by a normal distribution whenever the sample size is large enough to satisfy these two conditions. We'll see this in a second. When those conditions are satisfied, the probability distribution of x in the sample proportion notation, x out of the sample size, like 14 out of 72 or whatever it is, can be approximated by a normal distribution because n is a constant. The sampling distribution of the sample proportion can also be approximated by a normal distribution. Okie dokie, it's a normal distribution. And so here's a problem, and then you're going to see us apply that, right, with our sample size of 30 and the population proportion of 0.6. Now, why they give us the population proportion, right, so that we could solve this right here, and we're doing a sample to get the sample proportion of the population, and then trying to figure out if the sample estimate is a good estimate of the population proportion. I don't get it. That's where that just seems a little bit, I said we're going to see a little bit of wonkiness about this, but that's the wonkiness. If you already know the population proportion, why are you pulling samples to figure out the sample proportion to estimate the population proportion? You already know the population proportion. Why try to estimate it with a sample? proportion. So whatever. I guess it's just like this is the stuff when you're learning, you're doing it to learn, and there's more nuances as you get further into it. So, you know, we know the population proportion of employees who participated in the management training program is that. What's the probability that a simple random sample of 30 employees will provide an estimate of the population proportion of employees attending management program that is within plus or minus 0.05 of the actual population proportion? So the first thing we do is see if we could satisfy this condition. And if we satisfy this condition, the sampling distribution of the sample proportion can be approximated by normal distribution when these two conditions are satisfied. And so here we have in 30, the population proportion 0.6, 18 is greater than or equal to 5 because these are our conditions, right? This has to be greater than or equal to 5. And then also we have n times 1 minus p, n times 1 minus p is greater than or equal to 5. And so we have 30 times 0.1 minus 0.6, or 30 times 0.4, and 12 is greater than or equal to 5. So we could say here that this is normally distributed, and when we do that, we're able to start doing a normal distribution. So the formula for calculating the standard error of the proportion, which is the standard deviation of the sample proportion, the formula for that is this. And so we could calculate that right here, and we get that standard error. And that standard error is this value, so that's notated right there. And here's our expected value of the sample proportion right there. And we want to know how much is 0.05. So we're going to go from 0.05 this way and 0.05 this way. So we're going to go from 0.55 to 0.65. Does that make sense? Because we're going 0.05. So we're looking 0.05 on each side of that. And then we want to see if this is a good, estimate of the population proportion. And so when we do that, they did that with Excel here. With a mean of 0.6 and standard error of this, we can use Excel's. So here's you put this formula into Excel, and the value is 71.2. We could also do it the way we did it up here. So I'm just going to grab this, boom, and bring this down here. And there's the Excel way. So now we're going to do it this way, okay? And so our standard error is going to be, so we have n equals 30, and we're just doing n equals 30, and then I'm just thinking this through here, so n equals 30, so I'm just going to take this out. Not sure if we need this over on this side yet, and we do have n equals 30. Okay, sample size is 30, and again at 30, that's that kind of magic number where we start to get normal distribution, and we saw that all the way back up here. So in most applications, the sampling distribution of the sample mean can be approximated by a normal distribution whenever the sample size is 30 or more, and that takes us to the central limit theorem. Okay, so that's why it's like you see sample sizes where it's like, hey, this is 30, and so there it is where it's 30. And so we have a sample size of 30, and our standard error, how do we calculate our standard error? Our standard error is going to be p times 1 minus p over 30, square root that. And so here we're going to have our standard error is going to be different, and it's going to be p, which is 0.6, and it's 0.6 times 1 minus p, which will be 0.4, so that's going to be 0.24. So 0.6 times 1 minus 0.6, and that's going to be divided by 30, I think. Isn't that right? It's going to be divided by 30, and then we're going to take the square root of that. So we're going to take the square root of all of that. And so when we do that calculation, we're going to get 0.24 square root. We're going to do the square root of 0.24 divided by 30. And when we take 0.24 and we divide it by 30, we're going to get that number. I'm going to copy that. So I'm just going to bring that in here and put that as equal to square root of this. Oops. And I'll make it smaller. And now if I take that and put that into a spreadsheet right here, which we have this, and I'll just drop that in right here, right there. Square root of that is equal to that value there. So I'm going to copy that, and then bring that back over here, and I'll say that is equal to that value there. So there's our standard error, and yeah, I guess let's leave it like that. So that's our standard error. So now that we have our standard error, we can start to think about our z-scores, and instead of these values here, this time we're going to be going from what is it, 0.6, and it's going to be 0.05 each way. And so 0.6, it'll be that's low, it's going to be 0.55, and then this one's going to be 0.65. And then we're going to calculate our standard error, which is going to be this point minus, it's going to be 0.55, 0.55 minus 0.6, minus 0.6, minus 0.6. And that's going to be divided by this right here, which is our standard error. Because standard error is the standard deviation for the sample point estimator, whether it's the sample mean or the sample proportion. And so there is that formula right there. And when we do this formula here, we get that. So I'm going to put that in here like that. And when we go look this up, that's our z-score right there is 0.559. And when we go look that up in our z-table, negative 0.55, 0.559 is, you might as well just say negative 0.56, and it's going to be 0.2877, 0.2877. So what that shows you is that 0.55 from here over 2877 is the value we came up with. When you calculate it with Excel, you get 2880. But from here to the left is 28.8% of our data, or we came up with 28.77% of our data. And then to do the same calculation here, I could just copy all this like so and put that there, and I'll make this 0.65 because we're on their side, and I'll copy that up here and paste it in, and we get this, and I will put that there. And so when I look up 559 or 56 on our z table, positive 0.56, it's going to be 71.23. And so we're going to have 71.23. And when we take 28.77, and we subtract 71.23, we take the big one and we subtract the little one. So we start with the big one. That's all the data from that point to the left, and we're going to subtract away this stuff is what we don't need. And I'm going to do that and drop that into Google, and we get this much. Whoop, whoop. And I'm going to put that right there. And so that is, I'll put it right here again, 42.46% of our data is in this middle area right here, 42.66. So it's 71.2 minus 288. And that's really weird how they wrote this, because the answer is then 42.4240. I guess they're just explaining it, I think, left to right, read left to right. And we had that's the standard error of the sample proportion. And but that's the data right there. So we'll have what percentage of our data, right? 42.46% of our data will be right there. And so when we look at this, we got 71, they got 7120, and we got 7123. And then 7120 minus 28.8 is 42.4. So entering the formula, so the probability of the sample proportion being in the interval from this to that is this value right there. The sample proportion, I'm just wondering if that's the population, should be the population one. But so that's how you do the calculations, and that's how you do it for sample proportion.